Although fMRIprep runs your data through a standard preprocessing pipeline, it leaves out some steps. For example, you may remember from the fMRI tutorials that smoothing was one of the preprocessing steps, usually one of the last ones. Smoothing has been omitted by design. The fMRIprep developers don't make assumptions about how you will analyze your data in your first level analysis, and smoothing is an important determiner of how that will be done. For example, some MVPA studies don't do any smoothing at all before the first level analysis. Even for fMRI studies, the amount of smoothing is a matter of judgment, and experiments that are focused on larger cortical areas will probably want to use larger smoothing kernels. In order to make a valid comparison with the sub-08 data that we analyzed in the AFNI tutorial, we will run two final preprocessing steps: smoothing and scaling. The background to these steps can be found in the links down below. For now, we will learn how to apply them to the current dataset. In the AFNI tutorial, we used a smoothing kernel of 4 mm on the functional data, applied with the command 3D merge. First, navigate to the folder derivatives fMRIprep sub-08 func. We will run the following code to apply the smoothing kernel. This code is in the text box down below. It's simply a for loop that runs 3D merge on all of the runs. We will also have to scale the data to ensure that the mean bold signal across the run is 100, so that any deflections can be expressed in % signal change. We will also use each run's corresponding mask that was generated by fMRIprep. Again, the code for this is in the link down below. If you open up these images in AFNI, it should look something like this. And you can see that the deflections are around 100 in the time series. Since two separate masks have been created, you may want to combine them to use as a mask for your first level analysis. Taking the union of the masks will incorporate voxels in either mask, while an intersection will only keep those voxels that are common to both masks. In this case, we will take the union of the masks, which will be slightly more generous, by using the 3D mask tool command. If you open up this mask in AFNI, you should see something like this. Once we have these files, we are ready to run a first level analysis on the data, which we turn to in the next video. In the AFNI tutorial on first level analysis, we learned how to create a general linear model to estimate the bold response to each condition in our experiment. We will be doing the same thing here, extracting the relevant motion confound regressors from the TSV file generated by fMRIprep. fMRIprep creates a confound file for each run. For example, the confound regressor file for run 1 is called sub-08 task flanker run 1 des confounds regressors.tsv. If you open this file in a spreadsheet program such as Excel, you will see the following. You can see that the file contains many confounds, and you probably won't use all of them. If we wanted to replicate our AFNI analysis as closely as possible, however, we will need to find the motion regressors in the X, Y, and Z directions, which can be found here near the end of the spreadsheet under TransX, TransY, and TransZ, along with the rotations. There are several other regressors you could include, such as global signal, frame-wise displacement, and different component time series. Which ones to include are up to you. In any case, remember to use these regressors with AFNI's stim files option, which will not convolve the time series with a basis function, such as the href. Before we can run the first level analysis, we will need to convert the timing files. The steps for doing this are in the link down below, and what you need to do is go to this GitHub page, click on Make Timings, click on Raw, right-click, and then save this file into the flanker directory. Once you've done that, go back to your terminal, navigate to the flanker directory by using the cd command, and then type the following: bash make_timings. This will store the converted timing files for each subject in the func directory, which you can see by using the ls command within the congruent and incongruent.1d files. When you've generated the timings, navigate to the fMRIprep output directory for sub-await in the derivatives folder, and type the following: make stimuli, and then copy those 1D files into the stimuli directory. Before we can insert our confound regressors into the general linear model, we will need to do a few steps in Unix to format them correctly. fNI expects a separate regressor file for each run, with later runs containing a string of zeros equal to the number of volumes in the previous run. For example, if we had 2 runs with 146 volumes each, the second regressor file should have 146 zeros before the first confound regressor in the file. This Unix code is a for loop that will loop over each of those regressor files, translations and rotations in the XYZ directories, and then use awk to format them in a single column file. You don't need to understand the awk code for now, but just know that the result of this will be files that contain both the header and also just the file without the header. We will then create a string of zeros equal to the number of volumes in the previous run. In this block of code, we put in the variable nt the number of time points for the R1 scale image. This is the number of volumes in the first run before we start the second run. And then we use a for loop to create a 1 column of zeros. If you see this, it's simply 146 zeros in a single column. Now, we concatenate these 2 files using the cat command so that we create files in a format that can be read by fNI. This for loop again loops over all the different regressors and then concatenates those with the zeros file we just created if it is run 2. Now we have all the ingredients we need to run the first level analysis: timing files, pre-processed functional data, and a mask. To run this through 3D Deconvolve, go to this GitHub page and then click on do-decon.sh. Click on raw and then right-click anywhere, click Save As, and save this file into the derivatives fMRIprep sub-await func directory. Once you've done that, open up a terminal and type tcsh do-decon.sh and then the subject number, which is sub-08. When it finishes, you can open the stats file in the fNI viewer and overlay it on the template ENIGMA-U 2009 template. We can then set up our viewing of the analysis by doing things like only selecting the positive voxels, changing the contrast to incongruent minus congruent, changing the color scale to red to blue, and the threshold to p equals 0.001. In addition, we can use clusterize to only show those voxels in clusters of 40 or more. I'm doing a few extra things here, such as changing the resampling mode to make the clusters look a little bit less edgy. And then, if we go to the report interface, we can see exactly where and how big that cluster in the MPFC is. In this case, it's located down around here, and we can jump to the center of it. If we compare this to our previous results with fNI, with the previous results on the right and the fMRIprep results on the left, you can see that the fNI results appears to be a slightly larger cluster, but with a slightly lower peak. To fully compare the results between the pipelines, we will have to run fMRIprep for all the subjects, which we will cover in our scripting module in the next video. Now that you've seen how to pre-process and analyze an individual subject, it would be helpful to create a script that automates it for every subject. Previously, we used the fMRIprep single subject script that had a hard-coded subject number. To put this code into a for loop, we will need to include this line of code just below the first line. I'm going to edit this in the VI editor. Right here, you can insert this line of code subject equals $1, which is the first input that the user puts in. And then we replace 08 with $subject. And I'm going to write this file as fMRIprep_scripted. You can make the changes yourself, as I just did here, or you can download the script from the link in the box down below. To create our for loop, we will simply combine all of the code we ran in the previous chapters, making sure that they are in the correct order. Assuming you already ran the script maketimings.sh, you should already have a file in your Flanker directory called subject list, which contains a list of all the subjects in your study. The combined code for the for loop will look like this, which you can find on the Brain book. Each block of code is discussed in the previous chapters. The only difference is that we now use variables for input where appropriate. You can either copy and paste this code into the terminal while in the Flanker directory, or download this script from the GitHub page in the link down below. Again, making sure to run it from the Flanker directory. This will take a long time to run, maybe a few days, depending on the speed of your computer, so I'm going to fade out now. When the script is finished, do the same quality assurance checks that we covered in the previous chapters, examining each of these HTML files. If everything looks okay, then we are ready to do a group level analysis using the same approach as in the AFNI tutorial, and the code for this group analysis will look like this. As explained in the AFNI chapters, this code will run a one sample t-test on the inc-con beta weights from each subject's stats file. And it will be output in a folder called test.results. If we go into that folder and open up the AFNI viewer, we can overlay the results on the MNI 152-2009 template. I'm going to speed up here and set all of the parameters as I did for the single subject in the previous video. Using the same thresholding, you can see the results for fMRIprep on the left and AFNI on the right. The pattern of the results is very similar, and the strength of the effect is slightly stronger